So I'd like to thank the organizers, not only inviting me, but insisting that I should come, despite the fact that I also feel a bit off the topic. So I really enjoyed. I've been really enjoying to listen to very exciting talks from kind of different fields. On the other hand, you also have to bear with me talking about something slightly different. So I also feel kind like a bit of an outlier. Now, what I do mean with off the topic. So first of all, I left superconductivity quite a few years ago, and the only work I've been looking at topology issues is also a few years ago, and I still like the idea that the Dirac point doesn't exist. And since obviously spin-orbit coupling is opening a gap right at the Dirac band, it's actually Dirac who killed this Dirac point. So that's why I'm talking about things that are not related to topology or to the Dirac point. But I'm working quite a bit on graphene and also two-dimensional materials, but I'm looking at these materials from a completely different perspective. So for instance, how graphene is influencing other many body effects that we're looking at, like in spectroscopy. So let me get to my first topic and simply ask the questions whether we can see orbitals. There's quite a few experiments like photoemission where you can reconstruct the information from the photoemission experiment, how the molecular orbitals or atomic orbitals in the system look like. What I would like to suggest here is electron microscopy to be a source of finding molecular orbitals. So the question is, what do they look like, how we can see them, and here I really like to follow the idea of Peter Schatzschneider, with whom we are collaborating on this project. He's from the Technical University of Vienna, and this was still a collaborative project between the Austrian side and the German side. So what do we expect to see in a microscope? Well, and this is where graphene and two-dimensional materials come in, because typically in a microscope you have this multiple scattering between different layers of material, and here two-dimensional materials are perfect because you can just ignore this elastic scattering of what's happening here, but just focus on the inelastic part of the scattering. So still graphene wouldn't be a perfect material because it's so highly symmetric that you wouldn't see much, but if you look at defected graphene, like for instance replacing a carbon atom by nitrogen, or just leaving out one atom, so looking at a material with a vacancy, I would like to show you what we could see then. So let's focus on these two systems, on these two materials, and just have a look at the very simple electronic structure. So this is the density of states of the nearest neighbor atoms. On top you see the pristine material, where we have just the PC orbitals in the low energy range, and you have to go to pretty high energies in order to see also the in-plane components of the px and the y, which are degenerate. Now, if you induce a defect, then you see that the electronic structure is very much influenced. So this is also not new, has been seen before, but we can make use of it in order to distinguish between different orbitals in the microscope. So in particular, if you look at the low energy range, then you see in the nitrogen doped case we still have pz character in the low energy regime up to 2 electron volt here. However, in the vacancy and system, then you have to look at very low energies. This green line here, you see there's a very strongly pronounced py character in the density of states. Now if we go higher in energy, the system changes. Now we have a y character, the green line here in the nitrogen doped case, and the 4 to 6 electron region in the vacancy case is just dominated by pz character. And only if you go to higher energies, then also the x character mix in, so we have a mixture of x and y and also z in this energy range. Now, why is this important? Because from this we can compute the dynamic mixed form factor. So this gives us an idea about the intensity of the scattering, and these objects here that are entering this form factor, the cross density of states. So this is like the density of states, but with mixed character from the initial and the final state, and this is where the density of states come in. And now if you focus on the low energy range here and compute the picture that we see in an electron microscope, then we see quite a nice pattern. Okay, we even can identify here the space where the nitrogen is sitting. Now let's go to higher energies. The picture changes completely. Obviously here we have probed the Z character, now we are probing the Y character. And if you go even higher in energy, 8 to 6, then this picture is completely changed again, because here we see a mixture of px and the py in fact. So, well, to tell you the truth, what we did actually, we took these pictures, we sliced this area here and took many of these pictures and averaged over this area. Now, this is the summary. We have 3 different pictures that we should see depending on the energy scale. And actually, I should mention here that we're talking about electron-filtered electron microscopes, so we can choose an energy and then see what we should see. Now, let's go to the other case with a vacancy. If I go back and forth, then you see basically that this picture stays the same, but these two swap. And the reason for this is simply, as I told you before, in the vacancy case, we have the Y character here and the Z character here, and in the other case, it was the opposite. So the 3 pictures are really fingerprints of the 3 types of orbitals that we can observe. So let's keep this in mind and ask the question whether this is reality. I mean, so far I've just shown you theory, and I have to admit that I'm keep showing you theory because unfortunately when we came up with the project, there was SPICE working on this new generation of microscopes, but during this work, SPICE stopped this development, and so we still don't have pictures, real pictures, but I would like to convince you that with the best possible microscope that we have at the moment, we even could see them. So, is this reality or does it happen? So let's have a look at the pictures that we would expect from a microscope. So we basically mimic the lens system here, and this is a Techni F20, 80 kilowatt voltage here, and well, you see something, the pictures are different, but of course we don't have the atomic resolution that we would like to have. However, if you go to these abbreviation corrected microscopes, these Titan modern ones, then you really see that it should be possible to distinguish between these different orbitals. And yeah, hopefully there's someone, maybe even among you, who would like to give it a try. So let's switch gears, going to something else, and I would like to explore now how graphene affects other, let's say, objects as a substrate. I'll start with something which I also did a few years ago. You see band structure of a PPP. PPP is a polymer, polyparaphenylene, which actually consists of these rings, benzene-like rings that are connected to each other. The essence is, in such a one-dimensional material, we have a strong dispersion along one direction, but most important here is the electronic band gap, which is roughly 4 electron volt. Now let's put this molecule on graphene as a substrate and see what happens. That's the band structure. So the gray dots, they're not completely uninteresting for us at the moment. So it's just the band structure coming from graphene. But what is striking here is, if you look at the bands that come from the molecule, that the band gap all of a sudden has changed dramatically. So it's more than 1 electron volt difference. Why is this so? I mean, if you think about how you get the band structure, for instance, in the photoemission experiment, you can understand this very well, because what happens in photoemission, you shine in light with high energy, and this light kicks out an electron from the sample. So basically the molecule is getting charged, and this charge now starts to interact with graphene, which is underneath the molecule, and this interaction with charge and image charge leads to the destabilization of the HOMO and the stabilization of the LUMO. So in essence, you have a very strong effect on the band gap. Now, if you look at the electronic structure, the HOMO and the LUMO as a function of distance to the molecule, and they start from here, so this is very far away, then you see that the band gap, so the distance here, it corresponds to this here, and if you get closer and closer, the band slowly closes until it's ending up with this So let's get back. So if we put the molecule closer to the surface, then we see that the HOMO and the LUMO are changing until the band gap has reached this value. But if you look now at what happens on the density functional theory level, nothing happens, because here the conduction and the valence band basically are independent of the position with respect to the substrate. And this simply comes from the fact that they are poorly van der Waals bound, and semi-local functionals don't see the many-body effects. Actually, it's a true correlation effect. This is a dynamic correlation effect which causes this decrease of the band gap. Now, and this brings me actually to, now this is not working anymore. This is very interesting. Okay, so this brings me to my crash course on electronic structure theory. So what we have seen in the first example, the electron microscopy, we just looked at the density of states. So here, density functional theory was good enough. And density functional theory is this bit here. We solved the Concham equation, which is a one particle Schrödinger-like equation with an effective potential here. And the essence is that we, in Concham theory, we have replaced this interacting system of many body system of electrons by a fictitious system of non-interacting electrons, which gives you the exact density. So it's perfectly okay as a many-body theory, as long as you don't look at the band structure, because these quantities, the electronic states here, cannot be interpreted, because this is a fictitious system that we shouldn't interpret. So if you want to do better, if you want to look at the band structure, we have to compute what they call the quasi-particle energies. But we can make use of what we have learned below here, because I mean the Concham system is still a very good description of the many-body problem. But we have, in order to get these quasi-particle energies, we have to correct these Concham energies by computing the self-energy. And the self-energy now contains all the many-body interactions of the electron system, electron-electron interactions, but we have to subtract what we have already taken into account down there. So that way we get the electronic structure, and what we have seen before is a so-called GW calculation, G0W calculation, on top of an LDA calculation. So we have included these many-body effects, and you have seen only this many-body effects give you the proper result if you look at this band structure. Now, what I'm going to show you in the next, 20 minutes or so, is even more than this, because we're interested in spectroscopy. So we would like to look into neutral excitations, like the interaction of light with matter, and there you have to go even higher in the level of methodology. We stay with many-body perturbation theory, but what we do now is to explicitly account for the interaction between the electron that is exciting during this excitation process with the hole that is leaving behind. So, and this electron and the hole, they may form so-called excitons, electron-hole pairs. And in order to account for this, we have to deal with not only this many electron system that we can treat with these methodologies below here, but we also have to include this electron-hole interaction. So, and this brings me to a different topic. I'm switching the topic and go to switches. So we're looking at simple molecules, simple switching molecules, for instance, azobenzenes. These azobenzene molecules, again, they consist of two of these carbon rings, but now they have a nitrogen bridge in the middle. And if you shine light onto these molecules, they may switch into a different geometric state. And if you shine in other light with other wavelengths, they may switch back. So you can use this as a switch, but if you want to use it in a real device, you cannot do it in the gas phase where we know that it's switching, or in a liquid it's switching, but you have to bring it onto a substrate. And if you bring it onto a substrate, then very often it's observed that they don't switch anymore. And there are two reasons for this. One is that, and this is also a nice thing, because these molecules, they form very nice arrays of so-called self-assembled monolayers. But within these arrays, the molecules come very close to each other. And being close to each other, they are still van der Waals bound in the ground state, so they don't see much of a density overlap. But they're getting coupled in the excited state. And that means that they change the spectra of the whole thing. So I'm not going to talk about this. This is published in these two papers here. But I would like to talk about the other effect, because this is the interaction of the molecules directly with the substrate. And this is why, in essence, experimentalists typically put a linker here in order to increase the distance of the molecules with the substrate. But of course, we don't want to do it. First of all, it would be very cumbersome to compute for getting nothing, basically, because we really want to explore what happens, what is the effect of the substrate. So, and this is what we have done. So we put these molecules, in this case flat lying, on graphene. And graphene really offers us the possibility to explore this effect, because it's still small. Otherwise, if we would have to work on a semi-infinite a system here with many gold layers or whatever, it would be computationally out of reach. But the graphene gives us basically an idea what happens, and so we could explore this. So let's go ahead. What we see here is the optical spectra of the molecule, first in the gas phase up there, and then if you put it on graphene. So I've left out the excitations from graphene, because I really would like to emphasize on the effect what happens to the molecular excitations. So in essence, you see there's a blue shift upon absorption, so all the peaks here, they shift to the right side. And this is actually a competition of two effects. One effect we have just seen before. This is this polarization-induced lowering of the band gap, which actually should shift you everything to the left and not to the right. So there must be something else. And this something else actually has the same kind of origin like this band gap reduction, or part of it, namely the influence of the substrate. So if you think about this electron-hole interaction, it's an attractive force between the electron and the hole. And the only thing which hinders this coupling is the screening. So the stronger the screening is, the less bound the electron-hole pair will be. And so obviously, graphene, again being a polarizable medium, adds some more screening, and it screens not only the electron-electron interaction, which gives rise to the reduced band gap, but it also screens the electron-hole interaction. So this actually is a competing effect. In this case, the second one wins, and that's why everything is shifting to the blue. So, but there's also other effects. So obviously, since everything is shifting, the switching properties must also change, because you cannot excite with the same light that you have used to switch the molecule if the peaks are gone. Even some of them are even gone; they disappear. But there's also new peaks coming here, and these new peaks simply come from the fact that if you put the molecule on the substrate, we lower the symmetry, and then transitions which were not allowed before, they're becoming allowed, and you get even new features here. So let me explain you very quickly what is the nature of these features, and I focus here first on the very boring peak here, because it's a dark state, so you wouldn't see it. It simply has 0 oscillator strength, but still it's interesting to see what happens. So what I show here is the electronic band structure, and the color code here tells you what are the states that are involved in the transition. So obviously this is what's indicated here, a HOMO to LUMO, because this is the HOMO of the molecule and this is the LUMO of the molecule, and obviously this is a pure intermolecular excitations, which doesn't involve graphene at all. And this is what we see also from the electron-hole wave function, which it's a nasty beast because it's 6-dimensional and you cannot plot it. But if we fix one of these coordinates, and in this case we fix the hole here at the position where this star is, then we can see how far the electron reaches out from this hole. And you see, as I said, it's a purely intramolecular interaction. You see that the electron and the hole, they're sitting on the same molecule. That's why they are so closely bound, and that's why this interaction is very strong. Still, obviously, the additional screening of graphene makes the peak shift. Now let's go to the next excitation. This is a new one, and this is where graphene comes into play. You see, this is again a HOMO-LUMO transition, so the same bands are involved. But now we have here also some involvement of the bands. It doesn't hit the Dirac cone, as you see, but at least it's getting closer to this. And there you see this dispersion here comes from obviously some interaction of the molecule with graphene. And you also see well, that obviously the screening of graphene makes this exciton quite delocalized. So if I put a hole here, then the electron may even spread onto the next nearest neighbor molecules. That's why this binding energy of this electron hole pair is much weaker. Yeah, and last but not least, we can also explore the third excitation here. It's a HOMO -1 to LUMO. You see, it's not this band, but the band below here, but it's also pretty much an excitation of molecular states with not so much involvement of graphene. However, pretty much delocalized, because here the electron even travels to the next nearest neighbor molecule. Now, to keep the long story short, even if you manage to switch in this case, which is not quite clear because, as I said, the excitations change, you can do the same game for the other conformation, and we see again the same thing. We have a shift of these peaks and additional excitations coming up from the interaction with the substrate. So let me come to my last example here. We again stay with graphene, we stay with two-dimensional materials, but now we look into somehow stacked materials that are produced out of different 2D materials. In this case, it's boron nitride interacting with carbon. It's an interesting system because these two materials somehow are very different in nature. So we have graphene, which is basically a metal, a zero band gap material, with obviously, in terms of excitations, very small electron-hole interactions, so small Coulomb interaction. On the other hand, we have boron nitride, which is a large band gap material where electron-hole interaction plays a dominant role. So what happens if we bring these two things together? So the interesting thing is, and this has been found before, depending on how you pattern these materials, you can find some which open a band gap in graphene. And we have taken a few of them, and just look at one here. This is the band structure of the system, where we have one graphene layer, and it's stacked in between or sandwiched in between two boron nitride layers, but the boron nitride layers are pretty parallel on top of each other, so they have maximal interaction with each other. And this maximal interaction gives rise to the fact that the boron nitride bands, so the conduction band is formed by boron, split quite a bit, and also the valence band that's formed by the nitrogen is also pretty much split. And there you see the bands here in the low energy range. They come, of course, of graphene, but you see this gap opening. And I said you can play around with this patterning, but the band gap overall is between 0.3 and 0.4 electron volts. So there's not much difference. But as we will see, there's much difference in the excitations.
Are you considering the same lattice parameters? Or
they have nearly the same lattice parameters. We had to stretch the one a little bit or squeeze such. Yeah, there is some mismatch, but they're still close enough in order to form. So experimentally, they can be produced. So, well, just to tell you a little bit more about the splitting, since these boron nitride layers have maximal overlap, there you see here that if you look at these bands, for instance this here, and due to this interaction of these two layers, both of these, the density coming or is related with this band comes from both, or sitting in both of these layers. And the same is for the nitrogen here. If you focus on one of the bands, the density is also sitting in both of these layers. Now, from this picture, of course, you could anticipate already what happens in the excitations. Of course, since this is carbon character here, you would expect that the low energy range of the spectrum is dominated by graphene-like interactions, with some changes, of course, because now we have a band gap, so there is some exciton effects coming in. But anyway, and if you go to higher energies, then you would expect that in the near UV region, the spectra are dominated by the boron nitride thing. But the most interesting range, of course, is in between here, because here everything can happen, and I would like to show you what the character of these excitations is. So here we really construct something new, which is neither present in one or the other material, but just comes from the interface. So let's look at the more or less known things here. So it is excitons that I've chosen here, number 1 and number 2. I like to show you that they're really graphene-graphene interactions. And you see this from already the band structure. So again, with the color code, I show you what are the states that are involved in the transitions. And obviously, it's just initial and final states are both graphene, but in different areas of the Brillouin zone. And this is what you see also from the exciton character here. So if you put the hole in somewhere in the graphene plane, then you see that the electron is just sitting in the same plane, but it's very much delocalized, so there's not much of Coulomb interaction in between them. And if you look at the doppio, you see that this electron distribution is really spread over the whole region. So let's go to the high energy range now. We also see from this plot, now I'm focusing on exciton number 5 and 6, that obviously these are really excitations between boron and nitrogen. So the hole is sitting on the nitrogen, the electron is sitting on the boron. And looking at the electron hole wave function, you see this. So if the hole is basically based here on the nitrogen, then you see this is just a few neighboring boron atoms where the electron would like to go. So we have a very strongly bound localized electron hole pair here. And the exciton number 6, this is even more pronounced. So here only the nearest neighbor atoms are involved. Very, very, very localized interactions. And this is very much similar to the excitations that have been found before in bulk boron nitride. But now, in the very last minutes, I'd like to show you what happens in between. And there you see already, if I focus on excitons number 3 and 4, that here I have an excitation where the hole is on the nitrogen, in the boron nitrogen plane, but the electron should be sitting on the graphene. Here is the opposite. We have the hole in the graphene, but we can excite to a boron band. And this is the exciton wave function of these two excitations. So here, exciton number 3, the hole is at nitrogen, and the electron is sitting in the plane below. Here, exciton number 4, the hole is sitting in the graphene, but the electrons are going to boron nitride layers. So, just one more comment on this patterning, on this tuning. As I have said, if we don't stack this boron nitride on top of each other, so if you shift these two, then the interaction between these boron nitride layers is getting weaker. And being weaker means we have less splitting of conduction and valence band, and this means that one of these bands has a character such that the electrons are sitting here, and the other such that the electrons sitting here in the other plane. And now going back to the spectra here, we also realize that this changes the excitations in the visible range. Namely, in this case, it's the same, because here we have the electron, the hole sitting on boron nitride, and the electron is just in the graphene, so very similar to what we've seen before. But in the other case, if you put the electron on graphene, we don't involve both of these boron nitride bands, but only one. So in that sense, we can really tune these excitations here in the visible range. So this brings me to my conclusions. I just want to show you quickly what our instrument is that we're using. It's the most exciting instrument, of course, you can imagine, because it's a code called exciting. It's actually a full potential all electron code, so we can explore all electrons on the same footing down to the very low core states. We have density functional theory, many body theory implemented, and we have a very strong focus on excitations with all kinds of different theoretical spectra. With this, I'd like to introduce the team. You've seen some of the faces: Lorenzo Bardini working on the electron microscopy, Zhang Fu together with Katharina Kocki on the molecular switches, and Dima Nabok is our GW guy who was involved in several of these projects. And Andres Kulans, he is also one of the most responsible people for the code, speeding it up that way such that we really can treat such complicated systems with our spectroscopy codes. Wahib was a guest student from Algeria who did the work on the boron nitride graphene interfaces. I'd like to mention that all our data are uploaded to the NORMAD repository, so you can explore them if you like. And finally, I would like to thank you for your attention.
Thank you.